Okay, so we're going to continue today with memory reliability and security, and I'm going to give you a very modern perspective, modern in the sense that what's happened in 2020, essentially. So it's going to be a very hot off the press, if you will, coverage of essentially mainly RowHammer related issues, but I think you can also imagine other potential issues popping up, as I will allude to in this discussion. We're going to talk about data retention errors briefly again, and look into the future a little bit in terms of what the memory security and reliability perspective could be going forward, at least from the point of view of the hardware scaling perspective, because the issues we've been discussing so far are related to hardware scaling, right? And how that affects security and reliability. There's clearly a higher level perspective of memory security, which comes from protection of different data structures related to virtual memory, permissions, etc. I mean, we've covered some of that in digital design and computer architecture. If time permits, we may actually cover some modern things that are going on in that area as well. But right now we're looking at the perspective that's driven from the lower level, if you will. And clearly this perspective is extremely important because people like in the security community, as I mentioned in the last lecture, there has been a big shift towards hardware especially the last few years, instigated by RowHammer and then Meltdown and Spectre and then other things coming up. And people think that, I mean, the root of security actually should be in hardware, because whatever you put in software can be circumvented. But if you have some trust that's put into the hardware, such that provides some basic guarantees of security, hopefully you can build up layers of security on top of that. And if that trust is somehow broken, like we've seen in the case of RowHammer, then essentially you cannot rely on anything to build a secure system. And that's true for other things that you design also. For example, you can design a trusted platform module, which is essentially a root of trust in hardware, which you can trust. And if that has some issues, RowHammer could be one of them, for example, or some other problem due to security, because you may not have actually completely secured it, then all of the root of trust is broken again. And Intel, for example, has the SGX, secure guard extensions to its processors, which is essentially some secure memory plus secure operations you can do on that secure memory. But if that memory itself doesn't provide fundamental security guarantees, again, because of RowHammer, for example, then you cannot trust, you cannot essentially bank on the security that's provided by that hardware module. And in fact, people have shown that SGX trust can be circumvented completely with RowHammer because you can cause bit flips in SGX protected memory. And as a result, again, all bets are off because you cannot trust that memory that otherwise is supposed to be completely trusted, right? So that's the importance of these memory security reliability lectures. And I think this is the last lecture that we will have on this topic, and hopefully we will move into computation in memory in the next lecture. Okay, so hopefully that gives you a perspective. Okay, now let me start. I guess we've been talking about these 4 key problems, and now, as I mentioned, we've been focusing on fundamentally secure, reliable, and safe architectures. And we've talked about RowHammer in the last lecture. We've talked a lot about it, actually. We've gone into a lot of detail, and you've seen some security implications of it. People have taken over systems in many different ways, and new attacks are appearing, as I mentioned, both in the software community, software security community, which is interested in hardware. And we covered some interesting things about RowHammer. We basically tried to understand it by doing experiments on real DRAM chips. And I'm not going to go over it again. If you're interested, you can go over the last lecture and read the papers. We've talked about solutions, potential solutions. We're going to talk a little bit more about that today, especially given that existing solutions implemented by DRAM manufacturers are not foolproof. And I alluded to that also. And this is essentially where we are today. But if you would like to talk more about it, hopefully we'll have some brainstorming and discussion on this, because this is an open area, basically. Understanding, I think this is also, there's still work to be done in understanding. And it's very interesting, actually. There's more characterization work to be done. If you're interested, feel free to talk to me. This is an open area also. I don't think we fully understand RowHammer, especially in boundary conditions, for example. But solutions is something we don't have at this point. Surprisingly so, right? It's been 6 years since the original research was published on RowHammer, and we still don't have a solution that's secure. Let me put it that way. There are solutions out there, no question about that. They all have different characteristics, as we will discuss also in this lecture as part of the research that's done in 2020. But unfortunately, there is no solution that I could say at least is out there that's publicly available, that's secure. And this may be a good exciting thing to work on clearly, because this is a very hot topic today. Okay, we talked about this paper last time. Clearly, this is the first RowHammer analysis, and I've given you a bunch of references to retrospectives. And this retrospective is actually very, very comprehensive, as I mentioned. With my PhD student, Jeremy, we have looked at many, many different issues related to RowHammer, going from all the way from the lower level device levels to higher level issues in software security. So we cover a lot of work that has been done on RowHammer. If you're interested in something like that, this is a very broad perspective, and this may actually spark your interest in other things as well. I would recommend reading it. What this doesn't cover is what has been done in 2020, of course, since this was published last year, as you can see over here. And essentially we concluded that we want intelligent controllers to actually take care of an issue like RowHammer, at least with low overhead, right? And this is what we're going to again talk about a little bit more in this lecture. Hopefully it'll become clear that having some intelligence in the controller actually alleviates a lot of these issues, and it could be a solution to RowHammer, assuming you actually have a good solution created. Okay, and we also said that these controllers exist for NAND flash memory. Your SSDs that are, the SSD that's running on my computer right now, for example, has that solution. By the way, I forgot to start my recording, so maybe I should start my recording, although I'm going to rely on the Zoom recordings for YouTube lectures. Let me do it very quickly. Sorry about that. There should be an automatic way of programming this recording, as you can imagine. Okay, there you go. Okay, so let's get back. Basically, these controllers that are really sophisticated and intelligent exist already for SSD controllers. My SSD, for example, on my phone or on my laptop or in the data centers, they're all running intelligent algorithms to actually prevent faults, prevent errors, as much as possible, of course. And these algorithms are actually really, really sophisticated. And I'm going to give you a little bit more on this later on in this lecture. But when we cover flash memory, hopefully we will cover more. Again, we don't know we'll cover flash memory. Maybe we'll take a poll actually, because we have a lot of freedom to cover many topics in this course. And computer architecture is such a diverse field today that we cannot possibly cover all possible topics that are out there. Okay. So keep this in mind. If you're interested in flash memory, there's a lot of interesting thing going on here. But okay, let me give you the modern perspective that we did not fully have in the last lecture. What happened in 2020? Again, during the course of 6 years, a lot of interesting things happened. Clearly, there were a lot of attacks, and DRAM manufacturers said they actually had a solution that works for RowHammer. And essentially, there was this TRR, target row refresh, that was put into the DRAM standard, DDR4 standard, that basically said DRAM chips internally handle it somehow. There's no information beyond this. It's a bit frustrating actually if you're working on security, or it may be exciting if you're working on security, because now you want to understand what's going on by reverse engineering, right? But basically, DRAM manufacturers claim that they solved the problem. But let's see if that was actually the case. So there, I'm going to talk about multiple works. This I'm going to defer to later. This is actually a fundamental analysis of the scaling properties of RowHammer on the modern DRAM devices. You can see that it was published in June, and this work actually analyzes what's going to basically it analyzes many devices, more than 1,500 memory chips. It basically shows that RowHammer is getting much worse, and what can we do about it? So it's more of a I don't want to call a repetition of the study in 2014, but it's a much more scaling study to understand that what has happened to the problem in the last 6 years, fundamentally from a circuits and devices perspective. Have these devices gone better or gone worse? And what happened to the mitigations that have been proposed, many mitigations that have been proposed in both academia and industry, although industry is not fully covered here because there's not enough public information about it, except for the next paper that I'm going to talk about. So we're going to talk about this. Hopefully it's going to be very interesting, and hopefully this gives you an idea of what else may come if we actually understand the properties of devices much better going into the future. And this is what I'm going to talk about first. Essentially, this paper showed that the solutions that their manufacturers say are secure are actually not secure. You're still vulnerable to RowHammer. And of course, to be able to do that, you need to understand the device a bit more and understand how these solutions work. Just a little bit. You don't need to understand them completely, just so that you can induce bit flips by bypassing these solutions. And that's the idea over here. And we're going to talk about this to see how this works. And then this paper, which I'm not going to talk about as much, this is work that we had done with Microsoft Research. And the key question that we wanted to answer over here is a very important testing question, I think. Okay, you get the DRAM chip. You want to ask the question, is this DRAM chip vulnerable to RowHammer or not? It's a very simple binary question, right? Yes or no? And it turns out that this is a very difficult question to answer in the end. As you might imagine, based on the previous paper, right? Because previous paper showed that DRAM chips are vulnerable to RowHammer, even though there are mitigations in place. And this paper doesn't even try to reverse engineer all of those mitigations, but it basically tries to take a DRAM chip, put it on a real system, and tries to execute programs, of course, attack programs, let's say, programs that can cause RowHammer bit flips, and tries to ask the question, can we actually induce RowHammer bit flips? And it turns out this is very, very difficult to do. It's very difficult to actually have a good answer to the question. I hear some noise in the back. Maybe somebody is not muted. So if you could mute yourself, that'd be great. Okay, thank you. Yeah, and this is actually an open problem because actually it's an open problem in RowHammer, clearly. Basically, when you get a DRAM chip, can you quickly do some testing, either at the system level using instructions, or at some FPGA, some sort of infrastructure to answer this question, am I vulnerable to RowHammer? And clearly there's a reason for this question, because this affects everything else, right? If you can say you're clearly not vulnerable to RowHammer, that's great. You can provide a lot of the guarantees, and you can put your chip into really security critical applications without thinking about it, or while sleeping fine at nights, right? But we cannot do that today, unfortunately. And if you're interested why we cannot do that, you can read the paper over here. Essentially, at the system level, there are many instruction sequences that can cause RowHammer, but there's no best instruction sequence. There's some instruction sequences are better than others in terms of causing RowHammer, but it's not clear that there are not better instruction sequences to cause RowHammer, basically. That's one of the reasons why you cannot fully do it in the system level. And there are many other issues at the system level also, like reverse engineering the mappings of physical addresses, such that you're actually hammering the right rows that you want to cause the most bit flips, etc. Okay, so hopefully this is interesting, but this is an open problem, basically. RowHammer testing is very, very heavy in terms of the time it takes, because clearly you need to do a lot of hammers, and also the coverage that you want across an entire chip, right? Some parts of the chip may be vulnerable, some parts of the chip may not be vulnerable, and you really want to test the entire chip for the vulnerability. But if you can do this testing very quickly and, of course, very accurately, then you can now figure out which parts of your chip are vulnerable, how much vulnerable they are. For example, how many activates do you need to do to actually induce RowHammer in some rows, and then also, look at the heterogeneity in the RowHammer vulnerability, just like we did with the heterogeneity in the retention time differences in different parts of the DRAM chip, and use that heterogeneity for your benefit, right? It could be that some secure parts of the chip, secure data that you need can be mapped to parts of the chip that are not vulnerable to RowHammer, whereas data that you don't much care about, which you can have error vulnerability on, those can be mapped to parts that are vulnerable to RowHammer. So even though this paper doesn't really fully answer the question or doesn't provide a methodology that can answer the question perfectly, it's a good step in the right direction, in my opinion. So there's more to do in this area, clearly, and clearly there's research going on in that direction. Okay, so let's talk about Trespass. This was published, as I said, in May. It got the Best Paper Award in IEEE Security and Privacy, which is a top conference. This actually work done collaboratively with my group and Kaveh Zavi, who is now an assistant professor in the Information Technology and Electrical Engineering department over here, as well as folks at Vrije University in Amsterdam. These folks have a lot of experience in RowHammer from a software security perspective, actually. And we collaborated together so that we can actually effectively reverse engineer what's going on in existing DRAM chips that implement this target row refresh solution. So let me give you the high level perspective. Basically, the takeaway overall is this is the first work that shows that target row refresh protected DRAM chips are vulnerable to RowHammer in the field. And mitigations advertised as secure are not secure, basically. It's always good to do this kind of vulnerability attack research, in a sense, especially if you don't have people cooperating as providing security, right? Because DRAM chips clearly are used everywhere where computers are, and you really want manufacturers to cooperate. And there are multiple ways of getting them to cooperate, and one way is actually showing that the chips are vulnerable. And this, I think an important contribution of this is to introduce a many-sided RowHammer attack. We discussed, for example, single-sided RowHammer, where you hammer one aggressor row. And then we discussed double-sided RowHammer, where you hammer two aggressor rows and then sandwich one row in between, such that the victim actually experiences lots of bit flips more quickly. And this introduces many-sided. The basic idea is, as you can guess, you have at least 3 rows that you hammer as aggressor rows. And this will become clear that if you actually do at least n number of rows, you can circumvent the protections that are put into the chips, because some of the protections actually work by keeping track of how many times each row is activated. And if that table that keeps track of that information is of limited size, small, let's say it has 4 entries, maybe you can overflow it by actually doing hammerings on 5 rows. And now this table is overflowed. It cannot completely keep track of how many times each aggressor row is hammered. And as a result, it cannot take the preventive action to actually fix the issues that may be caused by those aggressor rows. And as a result, you're back to square one, which is the table is useless and you're vulnerable. Okay, TRR, I mentioned TRR as target row refresh. I'm going to talk about that solution. This is the solution that's advertised by the manufacturers. I mentioned earlier briefly, but I'm going to have another slide talking about TRR. Okay, so basically the idea is to hammer many rows that can, in such a way that you can bypass TRR, target row refresh mitigations. And as I mentioned, by overflowing these proprietary TRR tables that detect aggressor rows. And to be able to do that, basically, we partially reverse engineer, or this work partially reverse engineers the mitigation mechanisms implemented in DRAM chips and memory controllers. You can read more about that. I'm going to give you one example of it. And I think importantly, it also provides an automatic tool. This is called a fuzzing tool, for example, in the security community. You don't need to worry about the exact term, but it's an automatic tool that explores the space of many-sided hammers and creates many-sided RowHammer attacks, and does that effectively for existing DDR4 and LPDDR4 DRAM chips. So you don't want to clearly do this manually, but have an automatic tool that automatically tries to hammer a bunch of rows. Of course, it needs to select the rows intelligently such that they map to the same bank, in fact, same subarray. And then it sweeps the space such that it finds an n-sided hammer pattern where n is good enough, right? It could be, as you will see in the results, it could be as many as 19 rows that you need to hammer to actually overflow these internal protection tables and as a result, cause bit flips in real DRAM chips that are protected, that are supposedly protected. Okay. Yeah, keep the questions coming. This is, I think, answering your question, hopefully. Basically, this is the solution that's provided by DRAM manufacturers against RowHammer, and they basically advertise their chips as RowHammer free based on this solution. So how does it work? Again, there are not a lot of details, but at the high level, this target row refresh mechanism works by tracking activation count of each DRAM row in some way. And then by refreshing neighbor rows if row activation count of a given row exceeds a threshold. Okay, it's very simple. So this is very similar to the solution that we have discussed as part of the original RowHammer paper that suggested, okay, you can keep access counters per row. It doesn't have to be per all rows, clearly. If you're intelligent, maybe you can reduce the size of that access counter table. And then once one row's access count or activation count exceeds a particular threshold, then you refresh its adjacent rows. This is a solution that was known clearly, that was actually proposed by our paper in 2014. And we said that actually this is not a great solution because keeping track of these access counts is not easy in hardware, and that your table can become very large very quickly. We didn't evaluate it in a lot of detail, so we didn't actually go into that direction, but we proposed probabilistic activation, as you remember. But DRAM manufacturers actually took up on that, and basically they decided to put these tables inside their chips. But I believe that, I mean, I still believe that it's not an easy problem, actually, keeping track of activation count of all rows, especially when the number of activations is becoming smaller and smaller, as we will see. It's not easy. You may actually miss some rows that are activated. And if you want your tables to be small, which is really the case in DRAM, because if you think about it, this table needs to have an SRAM logic and also incrementer. So it needs to be, it occupies area in the DRAM process. Okay, we will go into this maybe more detail in the future, but DRAM process is designed for the capacitor, as I mentioned earlier. You really want to be able to pack as many capacitors as possible. And as a result, it doesn't go well with logic process. So if you want to put SRAM plus incrementer logic plus some other logic to keep track of the activation count and decide whether you insert into the table or not insert into the table, etc., this is clearly logic right now, and it occupies space in DRAM. And DRAM manufacturers, rightly so, they don't want to occupy a lot of space because this essentially is costly for them. And they decided to have limited size tables. It turns out their tables were too small, as we will see in a little bit. But that's how TRR works. And there are many possible implementations in practice, clearly. And DRAM manufacturers don't reveal how they exactly implement it. In my opinion, they go through this mindset, security through obscurity. Basically, you obscure things enough that hopefully you're secure, but you're secure only until someone figures out what you're obscuring, right? That's the key basically over here. So this we will get back to this. Basically, this paper shows that the security through obscurity is not a good solution in DRAM. Okay, so maybe exposing some details of the DRAM architecture, microarchitecture to the memory controller would have been a better option in this case. Okay, so there are multiple implementations of this. Some of them can be implemented in the memory controller also, clearly. But the memory controller has a fundamental problem that it doesn't know exactly which rows are physically adjacent to each other, right? And we've discussed this last time. This information is not visible to the memory controller because there's some internal remapping that happens in the memory chip. And this internal remapping is not exposed to the memory controller. Essentially because there's not good communication between the memory controller and DRAM for various issues like business issues and yeah, exactly. And in earlier chips, there were memory controller implementations, but they were also vulnerable. I'm not going to go through that. And some of them were actually resembling para as well, in the sense that they didn't really, in the memory controller, fully track activation counts. But they were much more probabilistic. I showed that actually in last last lecture's slides, I showed that an Intel memory controller does probabilistic adjacent row activation. It's very similar to Para. There are some differences. It's not as robust, I think, but it suffers from the fact that in the memory controller you do not know which DRAM rows are physically adjacent to each other. So as a result, it made a guess, and if that guess is incorrect, then you're not refreshing the right rows. Right? That's the problem. So you can still get bit flips. But in DRAM, TRR doesn't suffer from that fact. Basically, if you actually implement this high-level mechanism inside the DRAM, you can embed it inside the DRAM circuitry, and as a result, the DRAM manufacturer internally knows which rows are adjacent to each other, and they can refresh the neighboring rows correctly. So inside the DRAM implementation actually has a lot of upsides, and that's what the DRAM manufacturers have gone with. By the way, this slide is instructive because I think any memory that's vulnerable to some sort of read disturbance issue can use a solution like this. And again, memory controller versus a memory chip, that you will always have this issue of, does the memory controller implement it? Does the memory chip implement it, etc. So keep that in mind. We're really talking about trade-offs over here within the context of a particular mechanism. Okay, so let me give you some history. Basically, Intel actually, while we were collaborating with them, while we were working together, they actually filed some patents as well. And they basically, in 2013, even before our paper was published, it was rejected actually earlier, as we will discuss also later. They basically put this memory controller-based probabilistic solution into their server systems. And then in DDR4, they actually had a similar solution also. Later, DRAM manufacturers said, okay, we solved the problem. We have this in-DRAM TRR inside our modules. They're RowHammer free. You don't need to worry about it. As a result, Intel actually dropped this probabilistic TRR implementation from their memory controllers. Dropping means I think they just disabled it in their memory controllers, not necessarily got rid of the hardware. So they can always enable it again, in my opinion, if they've done the right thing. But basically, we're looking at this in-DRAM TRR solution in this work. So let's take a look at our goals. Basically, whenever you have this sort of solution, if you have an attack mindset, that's always good. You want to reverse engineer what happens in this in-DRAM TRR to demystify how it works. I'm going to give you an example of it, but the paper has a lot more details. And reverse engineering can be fun, as you can imagine. This could lead to a lot of insights in existing systems. And we wanted to bypass TRR protection. And as I said, up to 20 aggressor rows allows bypassing TRR, hammering up to 20 aggressor rows. And 20 is a lot, as you can imagine, right? But this shows you an idea, this gives you an idea that you can actually bypass things by hammering many, many rows. And as I said, there's an automatic testing or fuzzing tool, Trespass, which you can download actually online. It automates hammering pattern generation. So all of this is online. The paper has the link. You can download and you can test if your cell phone is, for example, vulnerable. Assuming all the limitations of the tool, of course. We will talk about this tool. This tool is also not perfect because we didn't completely reverse engineer every single DRAM chip. And we didn't completely reverse engineer even a single DRAM chip, in a sense. Basically, we did just enough to show that we can bypass the mitigations on a good number of chips from all manufacturers. Our goal was not to create the best possible tool to actually do RowHammering in existing chips that are supposedly protected against RowHammer. So this tool can still be improved, and there's actually a good direction. That's actually a good direction for potential research as well, because there are a lot of interesting reverse engineering issues in improving this tool. So basically, what we did in this work was to use our FPGA infrastructure. We used multiple infrastructures, but we used our softMC infrastructure, and this infrastructure, as you can see, is very useful. And we created a DDR4 version of it. I'm going to show it in the next paper. Actually, I didn't copy it over here, but this is the DDR3 version. And we created a DDR4 version so that we can understand what's going on with this in-DRAM TRR mechanisms. And if you haven't read this paper yet, I'd recommend looking at it, because this sort of tool is actually very useful for many things. So basically, intuitively, and also I think based on our reverse engineering experiments, there are two components of this in-DRAM target row refresh mechanism. As you can guess, there's a sampler which tracks aggressor row activations. And there are multiple design options, and we discussed them in the paper. You don't need to worry about them that much, in my opinion, over here. But basically, you can do it on a frequency-based sampling. You can do it time-based sampling, and you can do it some random sampling. Clearly there are different guarantees that are provided based on these, but frequency-based records every nth row of activation. Time-based records first n row activations, and then maybe repeats this time again. And then random records based on a coin flip. Okay, you can imagine many other potential ways of sampling as well. Of course, the key in sampling is you don't want to miss activations to rows that are actually being hammered. If your sampling is too infrequent, or somehow it has a bias, and somehow it misses those rows that are really being hammered, then you have a problem. And there may be issues in the sampler, as you can, if you read the paper. And regardless, regardless of whether or not it has issues in sampling or not, the sampler has a limited size. Meaning if you can somehow overflow it intelligently, then the sampler is essentially useless. That's the key over here. And we're going to overflow it with this many-sided RowHammer pattern. In a sense, it's a very simple idea. But it's good to think about this, right? It has not been done until this year. Okay, assuming the sampler works, there's an inhibitor, and the inhibitor prevents bit flips by refreshing victim rows. Victim rows could be physically adjacent rows, but it could be also rows that are slightly farther away, as we've discussed, right? So if you really want to be complete in preventing all bit flips, maybe you want to actually refresh more than 2 rows, not just the physically adjacent rows, but maybe the next physically adjacent rows, etc., etc. Maybe at lower frequencies, of course. And what DRAM manufacturers do, I discussed this last time also briefly. Basically, the latency of performing these victim row refreshes, it's squeezed into the slack that's available in the refresh cycle that happens. Basically, you send a refresh command in the memory controller. The DRAM manufacturer says it takes, I don't know, 300 nanoseconds, some number of nanoseconds, 300, but it actually takes 100 nanoseconds. Now you have a 200 nanosecond slack in terms of that refresh command, which the DRAM manufacturers can use to sneak in some preventive refreshes from this inhibitor. Once the sampler says, okay, refresh these adjacent rows of this aggressor, the inhibitor sneaks in those refreshes. That's the idea over here. And you can completely implement this in DRAM. And as I mentioned in the last lecture, relying on the slack is probably not a good idea, right? That's what I mentioned also. And I still believe that, because ideally we would like to get rid of the slack as much as possible to get higher performance and better energy efficiency out of our DRAMs. And also, I think if RowHammer problem gets worse, then you need to actually add more refreshes to solve the RowHammer internally in DRAM, and that will take more time. And at some point, you will, in my opinion, run out of the slack that you have. So this is not in my opinion, this is not a very well-principled solution, but it's clearly a solution that's implemented. Okay, so let me give you a case study of what we have done. So first of all, we wanted to look into how big is the sampler. So if you want to look at it, and if you have an FPGA infrastructure like we have, you can do what I just show over here. You pick n aggressor rows, and then you vary that n. You perform a series of hammers to each of the aggressor rows, let's say 8K activations to each of the n rows. And then after each series of hammers, you issue some number of refreshes, R refreshes, let's say. R could be from starting from 0 to however many you want. And we do this testing for some number of rounds. Basically, we repeat this hammers to n number of rows, and then refreshes, R refreshes, essentially to that place. And then we repeat it so that we can get some robust evaluation, because there's some noise clearly that happens sometimes. Even though you may not get a bit flip over here, you may get a bit flip over here, right? It's possible. So it's good to repeat the studies many times, because not everything is perfectly repeatable in the studies. Even though clearly, as I mentioned, whenever you induce a bit flip, you can induce that bit flip again and again in the same particular bit if it's vulnerable to RowHammer. But now we have a protection mechanism in place. It's not like there's no protection mechanism. Now we have protection mechanism in place, so it's better to actually test many times here. Okay, so hopefully it's clear. We're going to look at, we're going to vary n, and we're going to vary r over here. So how many times we're going to hammer, how many rows we're going to hammer, and how many times we're going to refresh that, let's say, bank. For your purposes, you can think about the bank over here. And clearly some number of activations is important. So we do enough activations such that we can fit those activations within a refresh within some number of nanoseconds. Basically, you can read the paper for more detail. So this is a chip from one vendor. There are similar results from all vendors, but basically what we're doing over here is varying n, number of aggressor rows over here, and varying the number of refreshes, r over here basically. And this is the bit flips. Corruptions mean bit flip over here. This is not a well-made slide, if you will, but it gets the point across basically. So clearly, if you're not, this is, of course, this is a sanity check, right? If you're not hammering anything, okay, this has a mind of its own. I need to stop this. Let me do it. Sorry about that. Sometimes when I copy and paste slides, it goes into this mode where it automatically moves animations, and I really dislike that, as you can imagine. But now I don't know how to actually get rid of that. Transitions. Okay. Anybody knows how I can get rid of this? Slideshow. Okay, yeah, slideshow. Okay, play narrations. Okay, that's the culprit. There's no need to play narrations actually. Okay, basically this is a sanity check. If you're not basically if the number of aggressor rows is 0, you're not hammering anything, then you should not get any bit flips, and you're not getting any bit flips over here. Okay, even though you're not refreshing anything, because we don't actually test for very long time intervals, and this is at room temperature, so retention errors are not really confounding things here. Okay, let's look at this one. We're hammering 1 row only. We're getting 2 bit flips if we're not sending any refreshes. So if we're not sending any refreshes, we're getting some bit flips. That's interesting basically. But if we're sending at least 1 refresh, we're not getting any bit flips. So this gives us an idea that maybe this mitigation mechanism TRR is tied with the refreshes. So you need to send at least 1 refresh to that DRM bank so that TRR mechanism kicks in, and as a result, it basically refreshes this hammered row that we're hammering such that it doesn't get bit flips anymore. Okay, so that's the first observation. I'm going to draw it in a little bit. Okay, let's do 2 double-sided hammering. So this is double-sided hammering. We're hammering 2 rows. Clearly, if we're not sending refreshes, we're getting a lot of bit flips, right? If we're sending 1 refresh, then we're getting a bit flip. So that doesn't sound good, but it's still low. So basically, we say that the TRR mechanism acts on a refresh command. So you need to send some refreshes, and you need to be able to send enough refreshes actually to get rid of the bit flips. Clearly, if you send 2 refreshes and hammering 2 rows, you're fine. You get 0 bit flips. But you need to send enough refreshes, and you need to send refreshes clearly. But if you don't send refreshes, the mitigation mechanism doesn't kick in. That's the first observation. So this is one way you reverse engineer things. And you could do this because we can turn off refresh using our infrastructure, as you know. Okay, now let's look at the more interesting parts. I mean, clearly this is interesting, but more interesting parts. Okay, what if you hammer 3 aggressor rows? Now you see interesting things. So you can see that we get a lot of bit flips. Well, this is not interesting because we're not sending refreshes, but if you send 1 refresh, you're getting a lot of bit flips. If you send 2 refreshes, the bit flips are going down, but they're never 0. So there's something going on basically. If you have 3-sided hammering, we can induce bit flips even though we send a lot of refreshes to this bank. And internally, the chip is probably doing these preventive refreshes. Okay, so basically we can bypass somehow this particular chip with 3-sided RowHammer, as you can see. But 29, these are small numbers, as you can see. Let's take a look at what happens even more. Okay, basically some of the reverse engineering observations are the mitigation mechanism can sample more than 1 aggressor row per refresh interval. And the mitigation can refresh only a single victim within a refresh operation. You can see the paper for more detail over here, even though this may not be visible over here. Okay, now let's take a look at what happens with 4 aggressor rows. We're sending 4, we're basically hammering 4 rows. Now clear the refresh counts are going up. Now this is a full matrix for you. So basically at some point, you can see that the bit flips become very high. For example, if you're hammering 8 rows as aggressor rows, even if you're sending lots of refreshes, the mitigation mechanism is not working. Right? You can see, for example, this is the this is not the worst case we tested, but this is where the this particular figure ends. If you're doing 9-sided hammer, even if you're sending 8 refreshes, it doesn't matter. Basically, you get a lot of bit flips. So basically, we've circumvented the mechanism. We bypassed the mechanism. You can say that, okay, these are small numbers. Maybe we're not fully bypassing the mechanism, but here the bypass is effective in the end. So basically, by sweeping the number of rows and number of refresh operations and aggressor rows while hammering, it kind of reveals the sampler size. So we can never be sure, of course, but we guess, for example, in this case, the sampler size is 4. And this is the same figure repeated from the paper. Basically, you can see more explanation over here. For example, when hammering 5 rows followed by sending 2 refreshes, we find 1710 bit flips. And this figure shows that the number of bit flips stabilizes for r greater than or equal to 4. And that's kind of true. Basically, here it's stable, here it's stable, here it's stable. It increases clearly because you're doing more hammering, but it doesn't change. The number of bit flips that you see doesn't change as you increase the number of refreshes over here, as you can see, right? For example, 4225 is very similar to 4218 over here, or 144 is very similar to 153 over here. So this implies to us that the sampler size may be 4. Okay, maybe it's not correct, doesn't matter. We bypass the sampler, or we bypass the mitigation mechanism. That's what matters in the end. Maybe we haven't perfectly reverse engineered what's going on underneath, but the mitigation mechanism is now ineffective completely because we've created an attack that bypassed it. Okay, so hopefully this gives you an idea of a security solution that's not fully secure, right? This is one example, and this is something that should not happen, in my opinion. Okay, these are some observations that I've already shown you from the paper, but this is also pictorially showing you 2 hammers. So we create a tool, and this tool actually does some exploration. You could actually imagine enhancing this tool with genetic algorithms, for example, or some machine learning algorithms to actually explore even better the design space. But the tool was able to, for example, come up with this 3-sided RowHammer pattern, which is interesting, as you can see. This is a double-sided RowHammer. You can see you're hammering this row, and there's a sandwich in between. But clearly you have victim rows over here. But then there's a sidekick row that we found. If you hammer this row, you can actually bypass the mechanism. Not necessarily the adjacent row over here, but you can see that the white rows are not hammered. The red rows are hammered over here. The blue rows are victim rows. But this row is a little bit farther away in the same bank. So our mechanism discovered this pattern, for example. If we actually use machine learning, in my opinion, we can discover even more patterns for many-sided RowHammer. But this is interesting to me. So this is the 4-sided. It's clear this is kind of expected, right? You hammer 4 aggressors where each pair has 1 row in between, right? And clearly this bypasses some of the mechanisms that are implemented. Okay, and clearly you can imagine 19-sided patterns also, but we're not drawing this over here. But this is one example with vendor C. This is what we do. If we actually, here we hammer using the default refresh rate. This is really an existing chip. We don't change the refresh interval. We don't do the previous study that we did for reverse engineering. You have a real chip. You have a real program that's running and that's doing this hammering. And you get bit flips, as you can see. So this is the same chip from vendor C that we reverse engineered. We find out that if you hammer 5 aggressor rows, you get bit flips. Now, we don't fully understand all of this over here, but if you do, 5 seems to be the magic number over here to get the most number of bit flips. Clearly, there's some other thing that's going on in the mitigation mechanism that's not fully reverse engineered that leads to still errors over here, and that doesn't lead to errors over here, you can see over here. But you can see that the maximum number of errors happens with 5-sided hammering. My guess over here is because what's happening is you're able to cause the maximum damage per row while bypassing the mitigation mechanism. Meaning you're able to activate as many times as possible to cause the maximum damage per row while bypassing the mechanism. If you go to higher numbers, maybe you're not doing enough activates. And maybe if there's some interesting patterns over here that we don't fully understand. If you're actually doing a lot of hammering, there's something that's going on with the internal mitigation mechanism that we don't quite understand. But also maybe your vulnerability to RowHammer increases because you're actually attacking this bank at many rows. So maybe there's some other noise effects that are coming into play over here that we have not fully understood, in my opinion. So that's why there's more research that needs to be done, even in RowHammer, as you can see over here. It's actually an interesting thought to think about the fact that you're actually weakening a bank by hammering 13, 14, 15 rows over there. Okay, so you can see that this actually happens for many other vendors also. This is, I think, one module from vendor A. You can see that the best attack, this is real chips. It's a standard specified refresh interval, real programs. You can see that the best attack happens with 11-sided hammering over here. And here you can see that the best attack happens with 9-sided hammering. You hammer 9 rows. Okay, so let me give you the key results. Basically, we found out that 13 out of the 42 tested DDR4 modules are vulnerable. That should be vulnerable, not vulnerable. So I'm going to correct it while maybe you're thinking of some questions. It's good to correct errors, as you can see, when they happen. And from all three major manufacturers, and you can see that the chips are vulnerable with different types of n-sided attacks, where n value varies over here. And again, you can think that 13 is small, but this is a proof of concept. We didn't try to come up with the best trespass tool. It would probably take more months, clearly more than what we've devoted. We worked on this for about a year or so. I mean, we could have come up with a much better, stronger tool if you waited one more year. Maybe this number would be 42 out of 42. I'm not sure. But proof of concept is important to show that there's a problem and the problem is not solved. And we also tested real mobile phones that implement LPDDR chips from 4 major mobile phone manufacturers. I think we tested 5, but we found out that 4 of them are vulnerable. And 5 out of the 13 mobile phones tested are vulnerable. Again, this is based on what we've discovered with our imperfect tool. And I believe the results are scratching the surface. The tool is not exhaustive. It's missing a lot of things. It's not looking at all banks, for example, etc. So there's a lot of room for improvement in the tool and uncovering more vulnerable chips and phones, and also understanding the RowHammer a bit more than prior works. Okay. So basically, the takeaway of this work is RowHammer is still an important and open problem, even though there are claims that are very strong claims from vendors that it has been a solved problem. Now we're back to square one. In fact, I think a lot of folks are worried, not just the vendors, but a lot of companies that buy DRAM and use DRAM in their phones and their data centers. They're worried because this happened. Essentially, trespass happened. So it's still an open problem. So it's very interesting to me, actually. And I think the second takeaway is security by obscurity is likely not a good solution. Now, I think if your solution, I don't completely believe this, frankly. I think if your solution is completely perfect and it prevents against RowHammer, maybe security by obscurity is a good solution, right? But of course, you need to somehow prove that that's the case if you want to actually take that route, security by obscurity. In the absence of that, I don't believe security by obscurity is a good solution. Okay, if you want to know more about Trespass, you can read the paper. And we're also very happy to talk because this is really an open research area, as you can see, and there's a lot more things to do. Interestingly, the DDR5 standard that comes after DDR4 standard has something like a TRR solution. It's called RFM. It's called refresh management. DRAM manufacturers, for some reason, don't like talking about RowHammer, as you might imagine why, perhaps. But essentially, they're not open enough. I think it's time probably that they became open enough that this is a problem. This is a scaling problem. We're not able to solve it easily. So let's let's work on it as a community to solve it, as opposed to hiding it and hiding it and hiding it, and perhaps creating even more problems going into the future, right? So that mindset has to change at some point, but we'll see if that changes, because there's a lot of ingrained business as usual that happens in I think the DRAM industry overall, which is a bit sad, as you can see, because all of these DRAM is going into our computers that is affecting our lives. Okay, so I would recommend you take a look at it, and if you're interested in doing research in this area, actually we have a lot of research topics. Okay, I see one question over here. Sorry, I missed the beginning of the lectures, but does the memory controller have enough bandwidth to hammer multiple rows? And the answer is yes. You will be able to squeeze in fewer number of activations to those rows, to each row, basically. Basically, you can you can think of it that way, this way. You have some number of activations you can perform within a refresh interval. Let's say the refresh interval is 64 milliseconds, and you can do an activate every 55 nanoseconds. You can calculate the number of activations you can do. 64 millisecond divided by 55 nanosecond, right? Okay, you can calculate that, let's say. Now you can choose to do those activations on a single row, which means that that single row will be activated that number of times, or you can divide it into 2 rows, double-sided RowHammer, or you can divide into 3 rows, 4 rows, 5 rows, 6 rows, right, or 19 rows. Now you have an activation budget that you're using intelligently, hopefully, to hammer many rows such that you can bypass the protection mechanism. That's the idea. I think of it this way, basically. You have an activation budget that's dictated by the refresh interval, and also the number of, basically the latency of an activate, the minimum latency between 2 activates. And then you can use it however you want to induce errors. You can decide, okay, I'm going to activate row X with 60% of my budget, row Y with 20% of my budget, row Z with 10% of my budget, and the other remaining, I don't know, 5 rows with the remaining budget equally divided, right? I don't know, maybe that leads to a better RowHammer. That's why I think exploring these with machine learning techniques could be good, especially in the presence of mitigation mechanisms. So that's a very good question, basically. And I think hopefully that clarifies the way to think about it. I think about it as really an activation budget you have and how do you use it. Okay. Okay, any other questions? Okay, let me, I think it may be a good idea to take the break, but before I take the break, I think I'll talk about some of the potential directions over here. Basically, there are multiple directions. As I said, building a complete Trespass tool is very interesting for sure, because that now you need to go into the guts of this Trespass mechanism or TRR mechanism and reverse engineer it better. And it's not easy because the TRR mechanism implemented is different. It differs from manufacturers, clearly. It differs between generations. And it also differs based on the best attack, differs based on the DRAM chip potentially, because DRAM chip's vulnerability, it differs basically. Different DRAM chips have different variation, clearly, as we've discussed many times, and their vulnerability is different. As a result, the best attack that you can perform on a DRAM chip differs from chip to chip. So this tool really needs to be very, very comprehensive and very, very intelligent to find the best attack, or to find an attack for a given DRAM chip, because an attack, let's say n-sided RowHammer, 3-sided RowHammer that works for one chip may not work for another chip, right? Actually, let me quickly, I was going to quickly go through the paper, but let's see. Can you see my screen right now? Can you see my web page? I need a yes or no. If
not yet.
Okay, so I guess I have not shared my entire screen. So let me do this. And then after this, we're going to take a break. So okay, let's do this. How do I do this? I have to stop sharing first, or okay, new share. I guess I could do new share. That's good. I'm learning something, but I cannot see my screen. Interesting. So I cannot do new share. So I'm going to stop sharing. Stop share. Screen share. Okay, Google Chrome. Now I can see it. There's some bug in. Okay, can you see my Google Chrome right now, the browser?
Yes, we can see.
Okay, great. So I'm going to click on this paper. That's how you can reach the paper also, as you can see. Okay, you can see my internet is extremely slow when Zoom runs. I don't know why. I think something happened over Zoom. I think lots of people in the world are using it as a result. Things are just slow, or maybe it's just my internet. Okay, so let's go to this table. Okay, this is the table I wanted to show you. Basically, these are the modules that we tested, the 42 modules. You can see that we're not able to discover a good pattern that causes RowHammer bit flips in the presence of these mitigations. But sometimes we are able to discover, you can see that 9-sided patterns, 10-sided, 19-sided patterns, modules from manufacturer A are quite vulnerable. But modules from manufacturer B are vulnerable more easily, potentially. As you can see, 3-sided patterns actually work quite well over here, but you don't get as many bit flips over here. And modules from manufacturer C, not all of them we found patterns on, but some of them we found interesting patterns that cause a lot of bit flips, as you can see over here. And even if you double the refresh, as you can see, we can induce bit flips in some of these. So doubling the refresh, which is an aggressive solution, you're doubling the refresh plus you have this in-the-amp TRR mitigation, and even then we are able to induce bit flips in some of these chips, as you can see. So the problem is out there, and as I said, the Trespass tool is not perfect, so we cannot uncover patterns that lead to bit flips, and we cannot uncover patterns that lead to a lot of bit flips in some of the chips, as you can see over here. But I believe this is just a matter of reverse engineering better, doing more exhaustive testing, and actually understanding basically these mitigation mechanisms a little bit better, and maybe also coming up with better patterns to do RowHammer, because this is something we don't fully understand today also. What is the best pattern to RowHammer with or without a mitigation mechanism? So with a mitigation mechanism, clearly the problem is tougher. You need to bypass the mitigation mechanism. But without is also interesting, because maybe you want to use your activation budget within a refresh interval to hammer different types of rows, different number of rows, rows of different vicinity of each other, so that you can cause enough disturbance around and within the bank. And I think this is something that I believe needs to be understood better. Okay, so there are a couple more questions. When you're doing n-sided RowHammers, do you keep the overall number of activations the same within the time period? Yes, the answer is yes over here. But of course, we tested a lot more things. Once you get rid of the refresh interval, you can test more. But we wanted to bypass stuff with the refresh interval, so we kept them the same. Okay, good. So I think one of the fellow students answered that, and his understanding is correct. Okay, let me see if I want to say anything else over here. Actually, I think we have a footnote over here saying this is basically the future work footnote, if you will. You can read it. These results do not necessarily show that memory modules from a specific module are more or less vulnerable than modules from other vendors. Similar to regular software fuzzers, it may be simply a matter of time and better strategies to find access patterns that lead to bit flips. Our testing is also not exhaustive due to limited testing time and resources to feed into this Trespass tool. Okay, I think I've given you all the conclusions and takeaways I wanted to give. If there are no other questions, I'm going to stop sharing.